So our next and final paper in this session, and in fact, very last paper of this workshop, is titled "A Dataset of Networks of Computing Hosts," and it will be presented by Omid. Omid, you will be presenting, right?
That's right, yes.
Okay, please go ahead.
Hi, everybody. Thank you. Thanks to the organizers for the conference. And yes, so this is a joint work with my colleagues at Cisco Secure Workload. So in industry, we deal with the large data sets, and it's always good to share and give back to academia. And I've done this at Google too. When I was at YouTube, Google, I made a data set of videos public of text and audio multimodal or multi-view. So here we are making data set of disjoint graphs of activity of applications. Customers are our own data, public. I am in the works to make it available at UCI machine learning repository. And yes, so the data set is a little too big, so I had to email them. They haven't come back to me. But let me know if you need, I expect in the next few days or weeks, it should be there at the UCI. I don't know what the process is. It should be short, but email me if you wanted to play with the data set and take a look at it. Yes, so I'll give a better background.
Omid, sorry to interrupt.
Yes.
Could you please put your slides in presentation mode?
Yes.
Yeah, okay, great.
Yes.
Thanks.
Sorry. Yes. Yeah, so I'll give a bit of background and describe what the graphs are, the semantics, and a little about their some properties of the graphs and some things you could do with them, and hopefully it'll be useful. Okay, so I'm a part of a Cisco Secure Workload, or formerly Cisco Tetration, and the team develops software sensors and pipelines. So these software sensors go to the hosts of a data center and report network communications among the hosts and possibly other things such as the processes running and metadata. And then we munch the data, our pipelines, and finally we give the data to the, present the data to the user. So let's say if you have 3 hosts and 3 sensors, our analytics engine extracts, let's say, a graph, and that's what we're going to talk about, a graph of the communications, and then presents it to the user. Applications are, monitoring and visibility into what's happening in your data center. And also this morning there was the talk of zero trust, so this falls in that space. So securing all the hosts, it can only, so that they can only talk on allow policies, only on certain channels, on certain ports. And that's has been shown that really slows down the spread of malware. So again, applications visibility and network monitoring and policy definition, who can talk to what, whom, which host to which host on which ports. All other ports are disabled. The flows will be dropped. And yeah, so policy enforcement. So I'll talk about the graphs, what they mean a little more in detail. And also, I'm not aware of such data sets except for one. When I looked at social networks and other types of graphs, the Los Alamos National Lab has lots of detail too with their graph of their enterprise. Hopefully we can add these are 22 disjoint graphs that we are making public. So yeah, hopefully we can add diversity to this sort of data. And also 2 of the graphs have a reference or so-called ground truth grouping based on the function of the host. So there's a grouping or grouping information that we provide. So also that's, you don't see that much ground truth with the networks and graphs. So that's good for evaluating clustering or classification algorithms possibly, and so on. Okay, so the semantics are simple. So we are providing graphs basically, and each edge is directed and is associated with the port and protocol. Then the nodes are IPs. Both ports and the IPs have been de-identified. So IPs are integers and ports are integers. All ports are de-identified. And so for a given node pair, there could be multiple ports. And also for most of the graphs, we provide the number of packets exchanged. These are hourly dumps, so hourly graphs. The port is the service port. There are actually two ports for TCP or a UDP connection. We have two protocols. And for each protocol, usually there are two ports. We are only reporting the service port. The other port is not informative. And actually, our pipeline has to figure out, usually for TCP, it's available, but it has to use different heuristics to figure out, for especially UDP. And sometimes the sensor misses it, which port is the service port. And there is some noise in that, some uncertainty. Their accuracy is probably in the high 90s. 90% of the edges are correctly identified. So yeah, so there is some noise with respect to determining which port is the service port. But that's basically it. So you can see here that nodes 1 and 2 talk on different ports, and there are 3 edges. And undirected, it would be just 2 edges, right? But directed would be 3 edges. And if you take the port distinction into account, port and protocol, you'll get 4. So these are the hourly dumps of the edge files. And you can see the first column is the graph. So the graphs are intermixed, at least for the 20 graphs. The 2 graphs that are kind of our workload is different files. And the second and third columns are source or the client node, the identified integer values, and the service node, and then all the ports and protocols they talk on in that 1 hour that our sensors saw. So this for the red dot is from my recording. I removed the recording, but the red dot is still there. So it's not very synced with my mouth movement. Yeah, so you can see that, for example, for graph G2 in the second line, there's only 1 port and protocol and 625 packets exchanged in that hour. While for graph 1 between nodes 3 and 4, you can see line 4, you can see many ports and packets. So again, edges are directed, but the number of nodes in this graph is 3. The number of undirected edges is only 2, but directed is 3. And the number of port distinguished, or we call it conversations, is 4. There are 2 different ports used, service ports used in this, 3 different service ports used in this graph, in this example graph. And the number of nodes that use 2 service ports, that provide 2 service ports, is at least 1 exactly. Okay, let's go to, so some properties of the graph. So that was it. Nodes are same type, but edges are associated with ports and protocols. And so the number of undirected and directed graph for some of the graphs are shown here in order of number of nodes. You can see that the number of directed, which could be at as much as twice the number of undirected, is very close to the number of undirected. This implies that there are not many cycles of length 2, or relations are not reciprocal. But the number of conversations, again, is higher. It's, again, the number of edges, the number of port differentiated edges. You can see that that's like sometimes some multiples of the number of directed edges. And here's the full table of many statistics. It just the 20 graphs plus our own 21st graph, which is our own insertion of our own workload, ordered by the number of nodes. And again, the diversity, you can see that although graph 4 is has the highest number of nodes in terms of size, but in terms of number of edges and many other measures, is not that big. The number of unique ports is only 287. Number of unique ports that appear, service ports that appear in 2 or more, is only 54. While graph 2 is fairly big in terms of number of edges or directed edges, and you can see that the degree, the median degree of nodes, and some, again, graphs that show diversities, like for graph G1, the median degree, although for all the other ones are fairly low, for graph G1 is the median degree is 18. And there's just other things like how many ports and unique ports and a provider or consumer and so on and so forth. the number of nodes that are clients with at least one port or 2 ports, and C1, C2, and so on and so forth. Okay, so here we can see that something about the longevity of edges or persistence of edges, and we can see that a lot of the edges are seen only in one of the batch dumped files. Okay, but you can see that that percentage goes down usually. But then there are some percentage, non-trivial percentage and non-trivial count of edges that are persistent. They appear in all the edge files. And so we show the percentage here, and the ports, the number of service ports that are corresponding to these long-lasting edges. So again, there's a diversity, but we can see that for many data sets, there is maybe a bimodal distribution. Most edges are not seen as much, but then there is a notable fraction that appear in almost all the batches, all the edge files. And here again, the last column shows the number of unique ports associated with those long-lasting edges, and the number of unique nodes, usually much less than the number of edges. And peeling is just basically a term I'm inventing. Is basically removing nodes that are not interesting, like degree 1 nodes, or nodes that provide a common service that have a high degree. So if we remove just degree 1 nodes, we get a peel 1 in the next table that I saw. And if we repeat this process and also remove nodes that connect to many, many nodes, the graph might shrink, and it gives you insights into the graph. So in this case, if we remove high degree and node 1 nodes together and then repeat the process, so if any other node becomes orphaned or has the low degree, degree 1, we remove it again and again and again, you can see that only these 3 well-connected cycles remain. And so if we do this last 2 columns show peel 1, degree 1 nodes only removed. If we repeat the process, we don't see difference, but you see the graphs, what percentage of the edges of the nodes are removed in peel 1. You can see for many graphs, a lot of the nodes are removed, even with just removing degree 1. And again, if you repeat this process, we won't get a difference. But if we remove both degree 1 and high degree nodes, I define it as 60% connecting to more than 60% of other nodes, we get a jump in removal. And again, you see some of the graph 99 or 100% of the graph is moved, but graph 2 is not very peelable, so only 45%. But in general, high degree nodes are important. So second column shows the highest degree node, what percentage of nodes it connected to as a service, in the direction. For peel, I just did undirected. You could do it for directed or port differentiator. For these first few columns, I'm using the direction. So you can see that what port and what fraction of the nodes. Again, these are insights into for the user to see what the common services are, remove them for subsequent tasks, and so on. Other tasks is clustering, naming, helping the user name if they don't have names for their host names, and again defining security policies. By clustering and grouping or community detection, they can organize we can help them. We provide the tools to help them, the customers, to define a tree of their organization, of their hosts, and then define the network policies. So here's just a quick slide on the number of on clustering versus community detection. And you can see that if you do community detection, you might get clustering based on neighborhood, of similarity of neighborhood, you might get these 4 or 5 clusters. But if you do it based on community discovery, then the bipartite graphs are put together as a whole. So you might get these 3. Depends on the task. Again, we provide guidelines when to do clustering, similarity-based clustering based on neighborhood versus community discovery. But yeah, these are some of the things you can do. So again, I didn't talk about one extra other graph. We in the paper, there are 21 graphs, but we are providing another graph of, again, our machines doing the build and the regression and test end-to-end tests. And that's for many months. And and also we are providing information for how to group them. Again, de-identify, we don't say what the groups are. We just give you the membership of the groups, but not the name of the groups. And yeah, so 2 of the graphs have ground truth information. And I went over several properties, connectivity. There's much more to be done. So hopefully some of you find this useful. Thank you.
Thank you very much for the.
And thank you for staying this long.
Yeah, so questions from the audience? From online participants, is there any question?
I did.
Yeah, please go ahead.
Thank you for releasing the data set, really useful. When we said like we are peeling off high degree nodes, so approximately what degree nodes were peeled off? Like was it?
Yes, so I just picked the 60% degree, 60% to other nodes that remain that can be peeled off.
Okay.
Some graphs you can see that the common service is like only 10%. It's still high relatively in terms of absolute, but yeah, in this thing I treated the graph as undirected, and I repeatedly peeled off the ones that have a 60% connection.
Sounds good. And what would be the objective of peeling? Like, is it to make the graph smaller for easy learning, or is there some other?
Yes, so it gives you insights into, like, for community discovery, you want you want to remove these high degree nodes. They violate the assumption of the communities are dense inside and the sparse outside. These high degree nodes connect to everybody, or almost a lot of the nodes, but also to the end customer. They want to know where their common services, shared services are. They might want to define a special group for them and define a security policy for those. So these peeling experiments give you some idea of what the graphs are. So for example, we know that these graphs don't have thin paths of length of one edges. Because when we do peel only degree one nodes, we see that we cannot repeating the process doesn't peel anymore. So it gives you insight into the topology of the graphs too.
Sounds good. Thank you. Thank you very much.
Thank you for your question.
Is there any other question? Okay, so if there is no other question, let us thank the speaker.
Thank you.
Thank you very much. So that brings us to the end of this particular session and also the end of the workshop. Thank you very much for your participation. Bye.
Thank you. Have a good night.
Thank you, everybody. Bye-bye.
Thanks.